Yeah, great to meet you, everyone. Thank you so much for listening to this talk. My name is Christine Yang, and I'm a cellist. So, as introduced, I'm a classical performer. So I play in and out of country often. Today I'm going to talk about the using AI in music performance. So we started this project 3 years ago, and that it's actually expanding. Um, so currently we have 4 projects. First one is music to bit, then that's more for audience, AI for audience. Second one is evaluator and companion. That's more like good influence on music performance. Then third one is automatic music transcription, how AI can benefit musicians. Then fourth one is a little bit different. That's further application of AI, the using music performance. So the ads, I have only 30 minutes, so I'm going to talk about only the first two. Before I talk about the first topic, music to bit, I would like to make a experiment, small experiment with you. So in this slide, I'm going to play two different cello music I recorded. Then while you listen to each of them, please imagine some kind of images or in the emotion or some scenery and so on, and please share with us. Okay. All right. This is the first one. Probably I need to. Right. That was the first one. Now this is the second one. All right, that's enough. So, what kind of images did you really think of? Anyone?
The first one sort of sounded like an 18th century court, um, royalty being entertained,
Oh,
France maybe.
very good, actually, imagination. Very nice. Yeah. How about some other imagination?
The first one I agree. And the second one reminded me Venice. I was thinking of Venice.
Venice. Second one, Venice. Wow. Yeah, that can be. Yeah. Good, wonderful. Yeah. Some other images or atmosphere, emotion.
The first one, the beginning of the day with
Energy.
yes,
Energetic. Yeah.
and the second one, melancholic meditation.
Melancholy. Yeah. Right. Good. Some other.
The first one is like more exuberance, like happier. Second one more nostalgic.
Yeah. So, based on the character of the music, yeah, somewhat that there are some common feelings, right? So, first one, image it can be more like the 18th century court. That's that little more specific, but a little more brighter, right? Brighter than second one. Second one can be a little bit somber and then like a little bit dark, somewhat. Yeah, I mean everybody's feeling can be different. I mean, I'm not pushing you to actually feel that, but just based on the music major and minor and tempo that actually the just common feelings first. Then how would AI generate relevant images? What kind of images that would generate? So let's watch that. So this is for the first music. good enough. Then this is the second one. Yeah, so were they close to your imagination? No, not much. Well, AI is not really perfect yet, right? Yeah, I mean, and those kind of things are a little bit more subjective, right? Yeah, but you can see actually somewhat the little more brighter kind of images, and the second one more like darker and somewhat tragedy images, right? Yeah, so those were generated real time, and this is about our first project, music to video. So this is about the real-time image generation by AI and concert. So basically, AI will analyze the musical elements from the music I play in concert. Then it will generate the relevant images. Our paper, Visualize Music Using Generative Art, were presented at the Triple E, the conference on artificial intelligence last year in Singapore. So I'm going to talk about that a little bit later. So how did I start this one? I'm just performer, right? I'm just really professional performer. So I really like performing with some other type of arts. So sometimes I performed with dancers dancing on the same stage. And some other times I projected some relevant images pre-made by me in concert. So why would I do that? Those are more like for entertaining audience, right? Entertaining audience. So if you see only my performance, then that versus actually some images with performance, then it's a little bit different, right? Yes. Then I start to think, how about having AI generate those relevant images automatically? So many students were interested in this project. So we started this project like 2023 spring. Yeah, so this is the workflow. So tools will capture the musical elements like the tempo, the range of the pitches, and various things. Then those features will become input to train the neural network machine. Then this trained model then will predict the genre of the classical music and also the emotion. Then it will form so text. So text prompt which describe music. Then we enter this text prompt in the generative machine model like Stable Diffusion. Then it will update the images while performance goes on. So those are a little bit more details. So we need to extract the features from the music, right? So we use various of tools, and those are examples. MIDI. MIDI can capture the pitch, duration, dynamic, then also actually timing and so on. But it doesn't really capture timbre. Do you know what timbre is? Timbre. Sound quality. Oh, sorry. I answered already. Sound quality. Yeah, sorry. Yeah, the second one is the Fourier transform spectrogram that captures more like frequency and time and intensity. But does it capture the exact pitches? No, right? It doesn't capture exact pitches. It's just all like just a little bit the subjective. Yeah, so they help each other. Then we also use constant Q transform spectrogram, which can capture the frequent notes. Frequent notes, then we will know the chord progressions, and from the chord progressions, then we will know the key of the piece. Then, as we did some small experiment, yeah, so some certain emotions can be represented by common elements. So, for example, happy keys. What would be the keys? Any musician here? Any music played? Oh, wonderful, yeah. Wonderful, yeah. Then what would be the key usually? Major key, yeah, usually, right? And how about the tempo? Fast, yeah, medium to fast, right? Yeah, so those are common elements. However, in classical music, we cannot really describe actually of this feeling, that exactly like, so there are so many exceptions, so many complicated actually, the descriptions and so on. But however, we still need somewhat common elements to train the machine, right? Otherwise, it will not actually present the really the so relevant images, right? So we use those elements, common elements. Yeah, then we wanted to categorize the emotion. So we listed the emotion and two axes of arousal and valence. Arousal means the intensity of the emotion, and valence means negativity or positivity of the emotion. Yeah, so for example, number one means more like the positive and uh, calm feeling, and number nine means intensive and also negative feeling, like the hateful, right? It doesn't really, yeah, it reflects. But yeah, so we used data set of songs with those emotional labels to train the machine. Okay, so this is music is an example. This one. So can you tell me if it's intensive or negative of the end, negative or positive? Yeah, how is it? Is it negative or positive?
It's intense.
Intense.
But I think it goes back and forth between positive and negative.
Right, right. Yeah, I think so too. And how about the positive? Yeah, positive and negative, right? Actually, and others. Any other answer? Do you all agree?
I thought it was positive.
Positive, yeah, right. I mean, human feeling can be really the subjective, right? Yeah. So, but our trained model will yeah predict this as more like a medium intensity, and also it can be positive or negative, so neutral kinda. Yeah. So then, how about this one? How was it? Slow, right? Slow. So, is it intensive? No, yeah, it's kind of the calm, right? Calm, and is it negative or positive?
Neutral.
Neutral, neutral. Yeah, so it's really hard to actually really the get really the single feeling out of actually one piece, right? But anyway, this machine we trained says the more like positive side and also like calm, right? Yeah, so that's the result we get. Then we wanted to have the corresponding arts, corresponding actually the result from the emotion and music. So art is very similar to music. So certain kind of emotion can be represented by common features. For example, the excitement and happiness kind of feeling can be by warm colors, bright, vibrant lightning, and straight lines and so on. And also calmness, serenity kind of feeling can be by pastel shade and some lightning and somewhat sparse touches. Yes, so we use these elements. Then anybody who used image generation program? Anybody? Yeah, right? Yeah. And if you change the prompt just a little bit, how is the result? completely different. Right. Yeah, right. So if we change the prompt just a little bit, somewhat the result has very different, right? So for example, if we use measure with waterfall in the woods as the prompt, then it will create, it's just example, but it will created more like the picture-like image. But if we use a beautiful mansion besides a waterfall and the woods by Joseph Stemmer, matte painting, those two, the last ones are just selected randomly, but it will create more like a deep and kind of mysterious emotional image, right? Yeah, so now actually prompt engineering goes. So we found prompt generation of the disorder, the musical period, colors, artist, lighting, perspective, and style. This order will generate the best representative image. So for example, romantic classical music is a musical period, and neutral and earthy tones, colors. And in the style of Claude Monet is artist, then soft lighting, low intensity lighting, wide shot, perspective, and matte painting style. So those two were just randomly selected though. Yeah, then it will create this kind of image. So this is the demo we made in the fall 2023. At that time, we were focusing on more like the more genre classification. So you will see the result. Still warming up. Yeah, so you can see actually many historical images, right? So the piece I performed was Bach Suite number 3 played. So yeah, it shows more like this Baroque chord and the Baroque or like yeah, those images. So this is our sorry. Yeah, so our future work will be, of course, we want to improve the accuracy of the images. So we need more data and of course, new features. Then we want to make it more interesting. So we want to make it more animated. So this is example. Oh. Yes, this is example. Yeah, so unfortunately, this was the not generated in real time. So it took time, but we want to actually generate so images, like not images actually the animated the video in real time. In current state of art, there's no actually this no technology which can do actually from music to video the real time. There's no data. So we are trying. We are trying now. So I'm a musician, so I always need to think actually what would be the benefit to musician, right? So the first audience can enjoy this informative and artistic images with music. And also musicians can promote our concert with those technologies. Then also not only younger generations, actually adults can approach classical music much better, right? Then also it's also possible that we can actually approach the more medical side. So it can also help hearing impaired people to understand the music in the concert, because hearing impaired doesn't mean they cannot hear anything. they are totally deaf. It's not that. So they can hear part of the sound. So they can understand better with images. So as I said, a paper was presented and IEEE conference last year. So this is based on survey, and survey had questions of which image best fits and the provided music clip. So among 5 images, each question, 2 images were generated by our system, and other two were picked by students from internet. And one was for cross validation to check if the participants have some kind of bias. Some people, for example, some people can have more like some people can choose more picture-like images instead of the more abstract images. Yeah, so we wanted to check that too. So the 50% is so almost 50% of images were more like for class validation and non-system generated, and then the other 50 was our system generated. Then this is the result. Your right side is the result. So interestingly, the 69% of images were the participants picked were our system generated. So interestingly, actually people like AI generated images. Yeah, so it's kind of encouraging that our system works. And so we are trying to train the machine the better, the more accurate, and with more genre and also more style and the composers. Okay, so this is the first topic, end of the first topic. Now the second topic will be the evaluator and companion. So before that, I would like to ask you, do you have any musician friends? Wonderful, good, good. Then my question is, what will be their everyday challenges as a performer? Sorry, maybe a little bit too, a little bit, like, yes, strange question, but anyways, yeah, but thinking.
Getting paid.
Getting paid, that's right, getting paid, right? Low payment, right, for musicians, especially, yeah, some places. Okay, some other practice, right? Practice, yeah, sure, yeah, wonderful. And some others?
Finding the right place and environment for practicing.
Right, right. Finding the right place and environment. That's right too. Yeah, wonderful. Good, good. Yeah. So, as performer, I was thinking actually, what would be the everyday challenges? Yeah, first one is the practice, right? Practice and the low payment too, in a sense. Yeah. So we need to learn new music constantly in short time, often. And some other times, actually, we need to bring back the old music on the hands in short time too. And according to the National Endowment of Art, 1/3 of the U.S. musicians are part-time. That means we need to balance up our time between jobs, right? So we don't have we are very busy, so we need to have very the concentrated and focused practice and very efficient practice time. Okay? Yeah, and second, injury. Injury is very common. Yeah, so it's like a sport. So when we actually play with the repeated motion, then it's very common to have injury, and sometimes it can come from actually bad posture if they are students, possible. Yeah, so that's the second. Yeah, so according to a medical research, 76% of orchestra musicians have experienced some kind of injury. It can be minor or severe. Yeah, it's just very common. And third, place, practice place, right? And especially when that we have a bigger group of the musicians. So when we have chamber rehearsal, then it's hard to find the time and place. So due to the time and the location, so some musicians cannot be there. Then rehearsals will not go very smoothly, right? So those issues, and of course there are a lot more issues, but yeah. So those are actually maybe representative issues. Yeah. So for solving those, that we are developing two tools: evaluator, companion. So those are two tools for helping streaming musicians practice in solo or ensemble. And fortunately, luckily, we got almost $1 million grant from National Science Foundation to support this research. And the purpose of the research is not really developing commercial tools. Actually, the goal is to figure out if, where, when, how, and how much AI can help our job. That's the goal. Yeah, so it's very interdisciplinary actually project. So first one is evaluator. It aims to improve individual practice and performance. And what it does is going to be it analyzes the musician's sound, so musician's input. Then it will compare to digitized score. Then it will detect the deviations in intonation and the rhythm. There are already some tools doing this. So for example, my pianist, I think it's made in Finland, and also Violi from China. Actually, there are some tools. So third one is actually a little more novel. So we will detect the incorrect postures by computer vision and machine learning to prevent the injury. So this is the workflow. So sheet music is converted to music XML file, which computer can understand. Then the evaluator can process all the information in score. Then also evaluator will process the audio input from the user, then it will compare. Then considering the score is the perfect performance, then there will be differences, right? So differences, actually we consider that as inaccuracies. So we will display inaccuracies like this in digitized score so that users can see. And also for computer vision side, so for camera, the will detect the posture, the user's posture, then it will compare to the correct model, then it will also display the inaccuracy in posture as well. So we can focus on a little more computer vision. So posture detection, right? Posture detection. And so I had to think of what will be the most common mistakes beginners or learners would make in cello playing. So this is a little bit more cello technique time. So when we play, when we hold the bow, this straightforward is actually correct posture. Little bit of pronation. This is better posture because we can actually put a little more weight on the strings. But if I play with this posture, is totally wrong. I cannot put actual weight at all. So we call that as supination, and it's very, very common mistake. And bow placing. So often we place the students that place the bow too high or too low. Too high actually is more common. So too high, and the high elbow and shoulder. When they get a little more so tense, then yeah, naturally they will have actually this posture that's not very good either. Yeah, so we need to train the machine to detect those the issues individually. So then we need to train when we train the machine. What do we need? What do we need for training the machine? Data set.
Yeah.
Yes, correct, right? Data set, right? Data set. But wood performers. Have you seen actually a YouTube video actually playing the cello playing with bad posture? Usually performers would not upload those, right? Actually, their reputation, right? Or even actually, they're not actually their students, the performance with bad posture, they would not upload. So this data is very, very hard to find. So I had to make myself. So I had to make actually 130 videos myself, and my yeah. Some students actually helped me a little bit. Yeah. So this first one is actually with the high elbow and the high shoulder, and then that one is with supination, and also actually bow too high, and yeah. So all those videos I had to make. Yeah. So we use the media pipe for hand and body detection. Hand and body detection. So so 21 nodes for each hand. So 42 nodes, right, for both hands. And cello and bow, we use the YOLO V8 to make those bounding boxes like that. So this is the demo, a little bit older. So as you can see, actually it's not very stable, right? Many boxes, too many boxes, and it's just shaky. Yeah, but it still actually detects somewhat actually bow correctly placed, bow too high, and so on. And supination, you can see, right? Okay, then this is better, little bit recent. Yeah, so this is somebody else. Now it has only one bounding box and one bounding box, right? And this is with bad posture. I don't know if you can see, it says supination, right? Supination and bow correctly placed. Yeah, but it's a little bit shaky still. Yeah, so we are trying to make it a little more stable, and we are even actually want to make a little bit of angle following the bounding box with a little bit of angle like this, so that they will actually detect also bow angle as well. Second one is companion. The companion will play the missing parts from the absent musicians in chamber rehearsal, following the musician's tempo and somewhat musical nuances. It will also respond in real time the verbal instructions. Saying is easy, but making is not easy, actually. Yeah, so we are focusing on two things for now. So score following and accompaniment. Score following means determining where the soloist is in the music, right? Then accompaniment means actually playing the corresponding part in the score. So yeah, so the way it would be, we are synthesizing each part by using MIDI DSP. Then the features will be extracted from the solo reference audio. Then also features will be extracted from the user's audio too. Then it will align. Then we know actually where the soloist is, comparing actually to the reference featured actually the spectrogram. And for each time step, the score follower estimates the soloist position, but still actually there can be some alignment error. And companion plays then synthesizes accompaniment in time with the score follower, but it can also have the accompaniment error. So we are trying to minimize this accompaniment error by the proportional integral derivative PID controller. So basically, if the accompaniment is behind, it will speed up. Then if the accompaniment is ahead, then it will slow down. Yeah, this is the user interface we currently have, and we will develop a little bit better. And of course, impact for musicians. So musicians may improve their skills more efficiently. Then also, when instrumental learning is a little more approachable, then we may have a bigger instrumental learning community, possibly. And the musicians in rural area can play chamber music without other human performers. So this is our the team VIP vertically integrated project. That's undergrad research team with a various background, the music and the art, and also of course actually ECE, the computer science and the technology and so on. Yeah, so many of them also actually the grad students. So Dr. Lu and Dr. Chen, are more technology side. Then when technology is somewhat developed, then we need to have the better user interface. So Dr. Chen, chair of art and design, will make that. Then after that, so the goal is to know if the AI can help musicians, right? So we need a lot of user studies, the huge user studies. So I and Dr. Yu from Utah Tech will do that. Then after that, we will have data, right? Data from the user studies. Then Dr. Brockman, the chair of music School of Management, will help on that, analyzing that data. Yeah, that was the end of the second topic. Is there anyone who are actually of the birthday month, in birthday month? Birthday is coming, or maybe past just of this month or something, or last month? Great.
Mine is passed.
Past?
Yeah.
Okay, great. How many days? And how many days passed?
6 days.
6 days passed. Oh, pretty close. Anybody else? No? Okay, so robot, our robot will play happy birthday to you. As you can see, still not perfect. We are starting this actually research from last semester. So this is the end of my speech. So I will give the mic button to Dr. Lu.
Thank you. Thank you. So today I will give a brief introduction about our paper published 3 weeks ago in EPFL AI, detecting music performance error with transformers. But before I go there, I want to just give you a bit background of my research since I started with Nani. How many years ago? I don't remember. But this was a book actually Nani wrote the forward for me. It was published 2 years ago, Low Power Computer Vision, Improve Efficiency of Artificial Intelligence. As you can see, for music, there will be a lot of applications where latency is very, very important. There have been studies showing that musicians can tolerate latency about 20 milliseconds. Means when one musician changes and we expect the other musicians to adapt, that delay is at most 20 milliseconds. If you beyond 20 milliseconds, then they really cannot play together. As you can see from this, this on the left side is the keywords, my research papers from ACN Digital Library. That's what this ACN thinks what I do research about. There's a lot of things about efficiency, power, and so on. And also, this is an advertisement of a computer vision competition I've been organizing for 10 years. Time goes fast. These are the sponsors over the 10 years. These are the winners. And this one is running right now, this month, 2025. And right now, we already have 32 teams internationally running low power competition. So let's talk a little bit about the milestone for artificial intelligence. Does anybody recognize some of the pictures? What's the first picture? Can anybody recognize? Fisher, Spassky,
Chess.
Chess.
Yes.
This was actually when I was at the Stanford. So Kasparov, when Deep Blue beat Kasparov in 1998. Before that, people said, if computer can beat human in chess, we are done. Artificial intelligence. Of course, after that, people say, no, we still have more problems to solve. Then this one was, yes, AlphaGo 2016. Autonomous vehicle, of course, everybody knows ChatGPT, right? But I would say music is even harder because music, you think about music, there are many, many different instruments, very often. And then they have a very wide range of tempo. If you think about people speaking, if we think speaking, understanding human speaking is hard, then understanding music can be even harder because different instruments playing simultaneously, with a very different tempo, and so on. So that's why I think this is a very exciting topic. I was talking to David just a little bit earlier. I said the music can be an edge for academia, since now it's really difficult to do some AI research competing with industry. But I think music is still early enough for academia to be very influential. For any of you interested in this technology, I'm also organizing a competition for IEEE. You are open next month. If you are interested, you can go to this website, aiformusicians.org, and then the winners will be invited to speak. In 2025, ICME will be held in France in June or July. So now let me talk about music. I'm going to skip a few slides. Music is really universal language across many different cultures. But I have a demo I want to show. I will go to the second demo first. Just skip the first one. So if you are a musician, please tell me what's wrong with this. How many of you have learned any music instrument before?
Yes. He's pages.
Okay, great. Anyone else? If you have learned, or you know anybody that has learned, basically, let's skip that. So one problem when learning instruments is if a student makes a mistake, the student may not be aware, or may not be aware of the type mistake, where the mistake is. And if the student rely on a teacher, the teacher doesn't come to the student's house every day. Usually maybe once a week or every 2 weeks. So we are imagining we want to have a music tutor that can detect mistakes. This is my student. I think the student plays better than I can play. What we have done is we classify mistakes into different categories. There are actual notes. The top one is the recorded. The lower one is from the score as a reference. It can be actual notes or missing notes, or actual and missing notes when the person plays wrong notes. Our method is better than existing methods. The main difference is we create an end-to-end training instead of using different stages. I will show you in a slide later. Also, our method is applicable for many different instruments. We experimented 14 instruments in our study. Most existing studies focus on only one instrument, and most of them focus only on piano. Some of them also can focus on violin. And our method can handle chord. That means you play multiple notes at the same time. As well as we can analyze them in the frequency domain and use spectrogram. We can also handle notes at the different durations, can be long duration or short duration. They will be reflected in the time domain. These are the instruments we studied. The study we perform is the music is generated by synthesis. The reason is very simple. We need a variety of data. It's not easy to tell musicians to make mistakes. And it's even harder to tell mistake where the mistake is. If we say, okay, please make mistake on this particular note, very often musicians will not do what you tell them to do, even forget to make mistake there, or they make mistake somewhere. Therefore, our data is computer synthesized. We can create the data precisely, the mistakes precisely. Most existing methods rely on some kind of time alignment, and that's the major challenge of existing methods. Means consider you have recorded music and the correct music, then we need to align them. Otherwise, you have error propagation. Means you have misalignment. Then everything else from there will be wrong. That's a major problem of existing methods. In contrast to the existing methods, our method does not need alignment. The A part is the existing methods. Basically, they will take audio recording and convert that through a transcription method, basically convert that into symbols. So that's the first major source of mistakes. Then they will compare these two results. That's the existing methods. Our method instead will not require alignment, and we also do not require transcription. That allows us to improve the accuracy pretty substantially. We take the synthesized audio and we take the audio, the lower part of the button is the audio recorded by the music student. Then we will compare these two directly and produce MIDI. MIDI means music instrument digital interface. Then we can determine what are the mistakes. This is the neural architecture. We take advantage of existing methods, in particular the vision transformer. If you can see from here, this is from the music student. This is the audio synthesized from the score. We convert into spectral grain. Then we tokenize them, send to a vision transformer encoder. Then we will send to auto-regressive sampling, so that allows to avoid the alignment part because they was use auto-regression to align themselves. Then from there, we go to the output that gives us the MIDI-like output similar to a piano roll. So that tells which note it should be. What are the major advantage of our method? First, by doing this, we can perform end-to-end training. We do not require alignment. And we also eliminate the need for transcription. As I said, that's a major source of errors in the computer part. Our method can also generalize into many instruments. As I said, I will study 14 different instruments. And then we improve accuracy by as much as 40%. I will show you next slide, the improvement. Also, as part of this study, we created a large data set. As somebody mentioned, data set is really limitation of a lot of studies we can see today. By using synthesized data, we can precisely determine where the mistakes are, and we can adjust the error distribution to mimic different kind of user behavior. This is only the 3 of the 14 instruments we studied. The average, most of existing studies, they can detect correct notes. Obviously, because now the overwhelming majority of the data is correct. That's why people put the data out there. Then in terms of missed notes, our method is much better than existing method. You can see almost 40% improvement of state of the art. The actual notes, our method is also much better than existing methods. I think I can skip this. The previous slide, the scores is calculated by F1 score. So if you study machine learning, you probably know F1 score, the definition. There are still a lot of things we need to improve. The first thing we need to improve is this does not handle dynamics. It's just simply is not part of our model. So we cannot detect dynamics. Second, we have not solved the problem of instrument separation. So if you have a piano and violin, then we just cannot handle that. I remember a few years ago, I went to a practice session of an orchestra. Kristen was playing with them. And then in the middle of practice, I heard the conductor told one musician said, "You are half a beat too early." And I was amazed. How can you detect that among, I don't know how many instruments simultaneously? This computer is still very far away from doing that. Also, currently we focus on the Western style music and instrument. To conclude, this study have proposed a transformer to detect music mistakes, and we enable end-to-end training without transcription or alignment. We have a significant improvement of the accuracy, but there are still a lot of improvement we need to make. So with that, I want to conclude and thank you for your attention.